Hello and welcome to Enough with the Science for another week of madcap tomfoolery dealing with scientific topics with myself, Joe, and Senan's over there.
Yes, hello, it's Senan here, and welcome to the third part of our two-part season on radio technology.
Yes, we're going to learn to count eventually. Now, this is definitely the last part, isn't it?
See, 3 comes before 2 if you are going in the opposite direction.
Well, if you're dealing with sort of sequels and prequels in Star Wars universe, it's 4, 5, 6, 1, 2, 3.
Yeah, that's right, yeah. And then we had Star Wars Andor, which was like 0.
Yeah, so, I don't know. Yeah, so who knows which direction numbers are meant to go?
Indeed, So anyway, we are on a mission to explain all the technological developments that made the mobile phone in your pocket possible.
Right, and so this week we're going from we kind of got as far as sort of radio stations and people broadcasting voice and sound.
So last week, we covered the whole business of how people started to broadcast sound on radio, and that opened up the doors of broadcasting and two-way walkie-talkies and all that kind of thing.
And today, essentially, we're going to jump from there to look at this amazing iPhone 15 or 16
we're
or 19,
going to cover.
There
was a whole pile of really innovative developments that occurred since.
Oh, can I just say, or Samsung, because they're equally good. Because we don't know where our sponsorship is going to come from eventually. So Samsung,
we'll be here all day for naming all the mobile phone manufacturers.
Well, like Samsung, iPhone. What's the Chinese one?
There's several Chinese ones.
It's a big one. There's got to be one big one.
Huawei, probably.
Okay, we'll take that one.
Anyway, so we're going to try and do a tour of all the technological developments that made this phone in your pocket possible. You pull it out of your pocket, you make a phone call, and you don't even think about the fact the quality of that call is going to be perfect. You're driving up the road at 100 kilometers an hour, and the call just keeps going fine, no problem.
You really don't think about that.
Yeah. And the only reason we don't think about it is because it just works. It's so good. The technology has gotten so good that we don't have to think about it. Yeah. So, essentially, I'm going to give you a quick introduction of all the things we're going to talk about today. The basic theme of today's show is the challenges of bringing radio to the masses. We've now got, at the end of last week, we had working audio transmissions on radio, but it's a different story when you want thousands of people to be able to simultaneously make phone calls. That's,
essentially because they need to broadcast as well as receive.
Yeah, exactly.
Where we left it, you kind of had a small group of people who are broadcasting and a big group of people who are listening.
Yeah.
But now everybody's a little radio station.
Yeah.
Look at us.
Yeah,
we've got a podcast.
Indeed. We are a radio station with no actual radio involved, but we'll ignore that for the moment.
But it must be involved. People are listening on their phone.
Oh yes, if they do actually download it over Wi-Fi, then their last leg is radio. Yeah.
Okay.
Yeah. That radio transmission is just going on inside in their house. Anyhow, so the first, I suppose, new innovation is, and we're going back quite far now, is transistors. Because prior to the invention of transistors, radios required vacuum tubes, large glass tubes that had fancy stuff inside in them that did things that radios needed to do. And transistors came along and replaced them. We're going to talk about all these things in detail, so I'm just going to mention transistors and we'll come back to it later.
Okay.
Much later on, in more recent times, we had the development of something called software-defined radio, and that made radio simpler because it eliminated a lot of the electrical circuits. Because you could now do a lot of the stuff that you used to do in a circuit, you could now do in software instead, as long as you had a powerful enough chip to run the software. We're going to come back to that. But probably the biggest single change that has made the modern mobile phone revolution possible is the change from analog to digital. So old-fashioned broadcasting and even AM and FM radio stations today are all analog. So they're actually sending a smooth representation of the waveform of your voice out with a radio wave. The move to digital brought huge improvements. So whereas our mobile phones are using digital, they're not using analog.
They're getting ones and zeros.
Yes, they're using our voice is converted into a pile of ones and zeros. Yeah, but that brought much better quality calls. It brought far greater capacity. In other words, you could squeeze more transmissions into less radio bandwidth, and it also, of course, now that you were sending data, you could send any kind of data. So it meant wireless internet was possible. It was suddenly possible to get the internet on your phone or to have Wi-Fi working in your house or whatever. So that was the move from analog to digital. The other thing, of course, if you have thousands and thousands of people all with their own mobile phone, how do you stop them from interfering with each other? Well, one of the fundamental developments...
They're calls from interference in your calls. Okay,
to clarify. It's outside the scope of this particular podcast to discuss any other kind of interference.
Okay, good.
Anyway, the idea of cells. So what that involved was thousands of low power transmitters scattered around the country instead of one great big transmitter in the middle of the country or something. Right. So that's cell technology. That was key to allowing thousands of users. Next problem was privacy. So radio transmissions, old analog radio transmissions, and even the initial basic digital transmissions, if you had the right kind of receiver, you could listen in on everybody else's phone calls.
Right.
So you needed encryption to prevent that from happening. And you also needed another method of making it hard for people to listen in, to eavesdrop, is something called spread spectrum. We'll come to that later on as well. But the probably biggest thing you need to do, I realise I've said a lot of things are big.
Yeah. But this is even bigger than the last biggest thing that he said.
Is now that you've moved on to digital, you need to be able to squeeze more traffic into less radio space. The more people that start using mobile phones and the more people that start getting the internet over their phone, you need to be able to squeeze more and more and more of that data into less bandwidth, because there's only so much radio bandwidth, and you don't want to run out of it, because then there'll be people who can't, when they try to use their phone, they can't use it. So several techniques have been developed to squeeze more traffic into less bandwidth, more digital traffic, more ones and zeros.
So in our dystopian future that we reference often on this program, is there a point where the radio bandwidths become full and nobody has...
Yeah, around about 7:10 this evening, I think.
Yes. Okay. It's all headed that way.
No, because there are... When you may be aware that mobile phone technology has gone through several different generations. 1G, 2G, 3G, 4G, we're up to 5.
G is for generation.
G for generation, yeah. We're up to 5G now. So 5G enabled the move to higher frequencies. So this was a block of frequencies which previously the technology made it difficult to use those frequencies on mobile phones, but now 5G has moved up onto those. So we've essentially made more bandwidth available than we had before, because we've moved up onto higher frequencies in addition to the old frequencies we were using. So but anyway, under the heading of squeezing more data into less radio bandwidth, basic data compression. It's a basic technique used by computers for squeezing data down to less size than it would if it was uncompressed. Multiplexing, which is essentially the ability to
go to many cinemas.
Yes, the multiplexes. No, it's the ability to have several phone calls going on in the same frequency at the same time, not interfering with each other, not hearing each other, etc.
Right.
There's a few different techniques for 3D modulation. So we spoke about different methods of modulating voice in radio. FM and AM, right, are the two classic ones. But you can think of those as two-dimensional. Somebody come up with this fantastic new three-dimensional modulation. QAM are the initials of it. And that just basically means that for the same radio wave, you can actually put much more ones and zeros into it. Then somebody else come up with a fantastic idea for multiple subcarriers. So traditionally, a radio transmission was a single carrier frequency, and the signal was modulated onto that single carrier. With OFDM, this technique is called, you have multiple subcarriers. So even though you have one transmission, you're actually transmitting on several different carriers at the same time, and different bits of it are going on different carriers. It's a technique that allows more data to be squeezed into less bandwidth. And then another lovely one is multiple antennas, known as MIMO, which stands for multiple in, multiple out. Again, a bit like the subcarriers thing, it gives you several antennas in the transmitter and in the receiver, so you can send more data in the same amount of time. Right. Now we've all got mobile phones and we want to go on holidays to France, or we want to go on business to Germany, and we would really like if our phone worked when we went over there. So the next big development was standards. A standardized system that would work in different countries, that people could seamlessly move around different countries and their phone would just work. And that's where GSM came in, the GSM standard, the Global System for Mobiles. And any country that's using GSM, which is nearly all of them at this stage, your phone just works when you go there. Right, the last issue that needs to be dealt with when you've loads of people at the same time using radio, and that is interference. There's always the potential, the more people you have using radio at the same time near each other, there's always the potential for interference. And we spoke about spread spectrum already in the context of privacy, but spread spectrum also helps to avoid interference. We spoke about the multiple subcarriers, OFDM. It's another technique that helps to avoid interference. Multiple antennas with MIMO, another one. But a really cute one that
We're still on the introduction here, right?
Yes, we're still on the introduction here. Another really cute one that is only started since 5G mobiles came along is beamforming. So in a traditional transmission, you transmit up, you send the signal up an antenna and it goes in every direction, 360 degrees all around. With phased array antennas, which are like a little lattice, a little array of antennas in the electronics, you can actually time the signal in such a way that the antennas only send it in one direction. And so there's a beam being sent directly to your phone from this mobile tower, and your phone is sending a directional beam back to it. So it's not going all over the place, potentially interfering with everybody. It's just going straight to the destination it's intended for.
Right.
So that's the challenge we have for today, to get through all that stuff.
I think we just did. Thanks very much for listening. Next week, here we go. So what's first? Let's go.
Right,
Transistors.
we'll go back to transistors, right. Invented in 1947 in Bell Labs by three guys, Shockley, Bardeen in Britain. So they were a replacement for vacuum tubes, and they had several advantages. First of all, they were much smaller. Like your average vacuum tube, like maybe 8 or 9 centimeters long, whereas most transistors at the time were 1 centimeter long. Now most of them are so small you can barely see them. They ran much cooler. So vacuum tubes worked only when they got to a real high temperature. Like if you touched one while it was switched on, it would burn you. And that heat had to be dissipated somehow. You know, that heat couldn't be allowed to build up inside in the radio equipment. Yeah. So
these are used for receivers.
Oh, and transmitters.
And transmitters.
Yeah. So the transistors ran much cooler, so they solved that heat problem. They were more reliable. Like vacuum tubes were a bit like the old-fashioned light bulbs. They wore out after a while and you had to replace them. Yeah. Whereas modern transistors effectively go on forever. They almost never die. They use far less power. So the vacuum tubes, you actually had to drive them to get them to work. You had to supply them at very high voltage, hundreds of volts. Whereas modern transistors just use a handful of volts. So much less power, and crucially cheaper to make and easy to mass produce. So you could make them far quicker and far easier with less raw materials and a simpler process than the vacuum tubes. The impact on radio. So before the transistors came along, a radio receiver was like a big piece of furniture. It was a big cabinet. Suddenly radio shrank into something you could carry around in your hand. And it kick-started a kind of a cultural revolution. People had portable transistor radios. They could bring music and news and sports with them wherever they went. And so it changed the culture. It gave people access to music and discussion, etc., anywhere they needed it. And it was the birth of portable music long before the iPod came around.
And it must have had them in cars. As soon as they put them in cars,
yeah,
that was game changer.
And of course, it evolved from there. I mean, transistors were individual components, but subsequently they were moved into integrated circuits, where you have this little chip that has thousands of transistors on it. So it's like entire circuitry inside in one tiny little chip. And you could miniaturize everything down to tiny. And it also reduced the power requirement. The smaller you made these things, the less power was required to drive them. So integrated circuits, which eventually became computer chips that we have nowadays. Right. Digital modulation. This is the big move from analog to digital. It kind of started in the middle of the 20th century, but it didn't really get going for sure until the 1980s. And in fact, the first generation of mobile phones in this country, and I'm sure lots of them, were not digital, they were analog, and you could listen to them quite easily if you had a radio scanner. So 2G second generation was when GSM became the standard, and part of that was that the signals were digital now, not analog.
So we're sending ones and zeros, and it was a global...
So what happens is the smooth waveform of your voice is sampled thousands of times a second, and a measurement is taken at that point, and you send that number at that point, and then a fraction of a second later you take another measurement and you send that number, and that's basically what's going on with digital transmission. So the numbers that describe the waveform in individual slices are what are being sent. Now,
to a layperson like me, that sounds like that would be a lot more information than the actual waveform.
But it's a different form of information.
Yeah.
And it can be put into a smaller slice of radio bandwidth, radio waves, than the analog wave can be.
Yeah.
But it also means that you get much higher quality, because if the radio signal is good enough to decode whether it's a 1 or a 0 that was sent, you get a perfect reception at the other end. Yeah. And the radio signal has to be really, really bad before you cannot figure out whether it's a 1 or a 0 you've received. So it's much more resilient to any kind of interference, and you get as long as the interference isn't awful altogether, you get a perfect reception at the other end.
It's a real Irish description of a numerical term, awful altogether. That's like how there's a standard for interference, and there's bad, pretty bad, awful altogether.
and don't even bother.
Don't turn it on. Don't even switch it on.
So digital also brought some other interesting things. So you could do, I mentioned earlier on data compression. So to give you a rough idea of what kind of thing, like there's a lot of different techniques involved, but a very rough idea is, let's say you're transmitting a piece of text and the third word is laundromat, which is a long word, right?
Yeah.
Anytime the word laundromat appears later in the text, you've only got to send W3, and the decoder at the other end will know that means the third word.
Yes.
So you're now using two characters, W and 3, to represent the big number of letters that are in laundromat. That's an example of the kinds of techniques they used for compression.
Right.
Then you've got multiplexing. So the thing about sending a digital conversation is that the amount of data is so small that you don't have to send it in a continuous stream. So as I'm speaking now, you could send a brief burst of data that might take you a quarter of a second to transmit it, that actually contains 2 seconds of my speech.
Right.
So you can be turning on and off your transmitter really quickly and just sending small bursts of data. A quarter of a second on your transmitter means the last 2 seconds of audio that was recorded. Now that's a kind of a crude. It's actually done on a tighter time scale than that.
My head hurts now. That means that the people who are listening are in the past.
Yeah. Well, they're in the past anyway because of the speed of light. Yeah. You know, or the speed of radio waves. Which
Okay,
is
let's not go down there.
Right?
Let's not go down that road.
Anyway, the point is, right, so let's say I have 5 transmitters all trying, let's say, simplify it, 4, right? 4 transmitters all trying to use the same frequency for 4 different phone conversations at the same time. Transmitter 1 can switch on for the first quarter of a second. Transmitter 2 can switch on for the second quarter of a second, and so on for the other 2. And that's time division multiplexing, which is what that technique is called. And so
don't ever ask me any questions about time division multiplexing, ever.
All you need to say is, I know all about TDM.
If that comes up on an exam,
just
I am
use
foobarred.
that acronym TDM and let's say he must know.
Yeah.
Anyway, there are other multiplexing methods, but that's just an example of one of them, right? Okay. We still need modulation, right? Like we had FM and AM for analog radio. We have what's called FSK, which is like the FM version of digital transmission, and ASK, which is analog keying. But there's another kind called phase shift keying, which is actually used on analog radio, but very rarely.
Phase shift keying.
Phase shift, the K in all of these. So FSK is frequency shift keying. It's a fancy way of saying modulation. Right?
Okay.
So anyway, phase shift keying is like very like FM. It's instead of with FM you're you're adjusting the frequency up and down a small bit. With phase shift keying, you're adjusting the phase of the wave.
Yeah.
Adjusting the phase of the wave up and down.
Right.
So it's a very close cousin of frequency keying. But the real star of the show is something called quadrature amplitude modulation, or QAM. It's essentially the other two, right? The FM and the AM are kind of like 2D. Well, think of QAM as 3D. Basically, it's, without going into the details, you're now fitting far more ones and zeros into the same piece of radio wave.
Okay, so
right? Yeah, so that's what that is. So then we get on to spread spectrum, which was originally invented. Now here's a little digression. Actually, it was invented back, I think, in the 40s or 50s, and one of the two inventors was the actress Hedy Lamarr.
All right.
So Hedy Lamarr was a well-known actress back in the middle of the century, and she had a keen interest in inventing and science, and she actually was involved in several inventions, including spread spectrum techniques. And the reason, what they were trying to do was prevent enemies from jamming radio control of torpedoes at the time.
Right.
Because
it's very specific.
Yeah, that's
and a limited audience, really.
That's the problem.
We talk about military people.
But the same technique went on to be used generally in radio.
Yeah.
But essentially, if what was going on was, they had a radio signal they were transmitting that was steering a torpedo, and the enemy had a huge big transmitter on the same frequency that was blowing the controller's radio signal out of the water. they were jamming it. Jamming just means transmitting on the same frequency with high power to block all the other signals at that frequency.
Right.
What spread spectrum did was it hopped around. So the transmitter that was controlling the torpedo spent only half a second on one frequency, then another half second on a different frequency, and another half second on, and so on. And only it and the receiver knew what the hops were going to be, what frequency we were going to go for number 2, what one we were going to go for number 3, and so on.
Yeah.
So both of them were synchronized, the transmitter and the receiver, to hop at the same time, to keep getting the signal. But the enemy wouldn't know what your hop pattern was going to be, so he wouldn't be able to keep changing his jammer to match. So
Yes.
yeah, so, and the same thing just works for ordinary transmission and reception, and it became a well used technique later on for ordinary transmission. But yeah, that was the history of that one. So it also allows multiple users to share the same frequency if they know what the hop pattern is, because you know when the guy beside you has hopped away from frequency number 1, so now you can use it.
Yes.
And so on. So yeah, it's an interesting technique for allowing. It's another form of multiplexing that we spoke about a moment ago, and it's used in Wi-Fi. It's used in Bluetooth. It's used obviously in mobile phones. It's used in GPS. So it's used It's used in lots of different things. Spread spectrum techniques.
Thanks, Hedy.
Hedy Lamar, yeah. So there's another concept that's kind of similar to spread spectrum. It's called OFDM, orthogonal frequency division multiplexing.
I'm at the point where I'm OMFG.
Anyway, we're not going to go into the details. Basically, instead of one carrier, it's loads of carriers simultaneously. Instead of one carrier wave, it's load of carrier waves with different bits of the transmission going on them. It's very robust, handles interference really well.
Okay.
And it also packs more data into the same signal.
Right. Now, see, that I don't really understand. I would have thought if there's more carrier waves, surely that would take up more.
But there's multiplexing going on. So even though I'm using 5 different carrier waves, I'm only using each one of them for like a fraction of a second, and something else can use them when I'm not using them.
Okay.
So yeah, there's all kinds of stuff going on there. Very interesting. This thing called multipath interference in urban areas. And because there's a load of tall buildings, the radio transmission bounces off several at the same time. So when it's received, as well as the main signal, it's getting all these echoes of the signal that have taken slightly longer to reach the same destination because they've bounced off all kinds of different things. It's called multipath interference. It plays havoc with radio reception in built-up areas. And this technique, OFDM, is one of the most important ways of preventing multipath interference. Anyway, software-defined radios. So traditionally, a radio had very complicated circuits. All of the different tuning and filtering and other amplification, etc., that you needed to make the radio work was implemented in a load of different electronic circuits. And along came software-defined radio, which was only possible after really fast computer chips became available. And what it does is a radio antenna in the air is not just picking up the one frequency that you're interested in. It's picking up all kinds of stuff that's coming through the air, all kinds of radio signals that are coming through the air. From space, from elsewhere on the earth, you name it. Mm-hmm. What software-defined radio does is it digitizes everything that's coming in that antenna immediately after it's received. So it doesn't do any tuning or filtering or anything with it until it all turns it into ones and zeros.
Right.
And then once it's a stream of ones and zeros, and you need, in order to do that, because there is so much stuff coming into that antenna, you need a really fast chip that's capable of digitizing that stuff really quickly.
Yeah.
But once you've converted it into ones and zeros, you can use software to do whatever the hell you want with it. So all your tuning is now done in software, all your filtering to remove unwanted parts of the signal, etc. All of it now done in software because it's all just ones and zeros. It brings huge flexibility to radios. It means the same basic circuit can be used as 5 different kinds of radios just by changing the software.
Yeah.
It means if you want some new feature that wasn't available when the radio was originally manufactured, you just give it a software upgrade and now you've got a new feature. So it just brings all this flexibility, and it means that previously, before software-defined radio came along, if you wanted one radio set that could receive loads of different frequencies, that was going to be expensive because it was going to have an awful lot of complicated electronics in it to handle all those different frequencies. Yeah. Now you can get the same thing much cheaper because it's just software. It's the same electronics regardless of what frequencies you want to listen to. Okie dokie. Cell phones. So In the old days of broadcasting, to set up a radio station, you had one like really powerful transmitter on top of a hill somewhere, and that covered hundreds of kilometers either side of the hill, right? If you want thousands of people who are located all over the country to be able to use the same frequency, that's not going to work because they're going to interfere with each other. Okay,
right.
So that one frequency can only be used by one person in the entire country at one time, right?
Okay.
The concept of cells is that you put up loads of small transmitters scattered all over the countryside. So there's maybe every 10 kilometers there's a different tower, different cell tower, different transmitter, and it means that say you have 3 of them in a row. Well, frequency A can be used on tower number 1. Can't really be used on tower number 2 because tower number 1 will hear that. But it can be used on tower number 3 by somebody else because tower number 1 won't hear tower number 3.
Yes.
So it just means that the same frequencies can be reused over and over and over again by different towers that are just, as long as they're not directly beside each other. And it just allows better reuse of individual frequencies. It does, however, bring on the problem of handoff. So if you're in a car having a phone conversation, you're moving out of the coverage area of one tower into the coverage area of the next tower.
Yes.
So some very interesting techniques had to be developed to allow you seamlessly be handed off without you even noticing on your phone call from one tower to the next.
Of course.
And these days, if you have a 15-minute phone call as you're driving down the motorway, you probably went through 10 different towers and never noticed any transition at all.
Yes.
And the early days of cell phones, that was a real dodgy procedure because the instruction went through the network for the second tower to pick you up. And before there was a confirmation from the network that the second tower had picked you up, the first one had dropped you. So sometimes your call just dropped because the second tower couldn't get its act together fast enough to pick you up before the first one cut you off. Now it's different. Now they're coordinated. The first one doesn't drop you until the second one is confirmed to it through the network that you are actually connected to the second one. So now the handoffs are seamless. 90% of the time. Very odd time you get a dropped call, but most of the time, it works.
It is magic. That is sort of magical, that element. Like traveling 100 kilometers an hour, you're like talking to someone on FaceTime at the other side of the world, and it just zips along through all the different towers, never drops.
Yeah. And I mean, so you say you make a phone call to a cell tower here. There's a radio link between your phone and the cell tower, right? The cell tower itself has another radio transmitter, usually a dish. So if you look at some cell towers, you'll see these round dishes on them. And that's a point-to-point link to some other tower that could be, 50 kilometers away. Yeah. And your call might go through 7 or 8 of those before it hits whatever cell tower the person you're speaking to happens to be connected to. Yeah. So you've all these separate radio links in the chain going on and you're completely unaware of it. It all just works.
But then if you're ringing someone in Australia, then it's going through satellite.
It could be going through undersea cables or it could be going through satellites. Yeah. I mean, these days, the problem about doing it through satellites is, certainly until very recently, you were talking about geostationary satellites, and those are really far out in space, which means that there is a delay. So the radio signal takes a while to get up there and a while to come back down. So undersea cables don't have that delay because the electricity that's traveling to them goes much faster than hitting this geostationary satellite. But these days you now have low Earth orbit satellite constellations like Starlink, which are so low down that delay doesn't happen. If your call was going through something like Starlink. Yeah. Right. I'll briefly run through the different, the 5 generations of mobile phones. We're coming close to the end.
Of everything. Of the world.
Of the world. Right. So 1G, the first generation of mobile phones in this country, I believe they were around about 1995-ish, I think, that they came in. Mm-hmm. So it was basically FM radio, analog radio, not digital. It worked, but it wasn't inefficient and it couldn't handle a lot of simultaneous calls and certainly no mobile internet. And there was no encryption, no privacy, and anybody with a scanner could listen to the calls. Then you had 2G. That was when GSM became.
I was going to say, why would you want to do that? And then I realised ham operator over here. Right? Okay. Yeah. Why would you want to listen to people?
Some people just liked the clandestine thrill of listening to somebody else's conversation, which was probably totally illegal and still is now, I'd say. Anyway, 2G came along. That was and that brought in the GSM standard. Originally, it started out as GSM was the standard in Europe, and something called CDMA became the standard in the US. now I'm not sure if CDMA still exists over there.
Well, I have to say, on a lot of levels, standards in the US have dropped.
But they are using GSM now. I know that for sure. So your GSM phone will work now. Whether they are also still using CDM, I don't know.
Yeah.
So that was digital. So now we were onto digital. Calls were encrypted. Text messages became a thing. So that was the first time you could send text messages, and that was really when mobile phones started to become mainstream. Like before that, they were like a big brick thing. Whereas now, after 2G came along, you got something that could more or less fit in your pocket. 3G, packet switched data was the main thing there. Basically, internet. It means that now you had internet access on your phone. It was slow, but it worked. You could do some basic internet stuff like emails, and if you were really close to the antenna, you might just about manage a ropey video call. So and it also brought in this more robust handoff between cells that I spoke about earlier on, where calls tended not to be dropped quite so easily. 4G, we got OFDM and MIMO. So much more robust and much faster data. And 4G is kind of the dominant, even though we have 5G now for the last couple of years, 4G is still the dominant technology really here and in a lot of countries, although there are 5G systems, most of the older phones are just still using 4G.
It's because of the phones rather than the system.
Yeah, well, it has also taken, the interesting thing about 5G is the cells typically are shorter range, so you need more cells distributed. So it has taken them a while to build out the 5G network because, you have to put up new equipment on all the cells and build a few new extra cells as well. But yeah, the 5G rollout is kind of more or less there now, but a lot of anybody who has older phones, they may still be on 4G. But and like it's perfectly adequate. It's for, you can browse the web on it, no problem. You can watch YouTube videos on it, no problem. You can do video calls. Like 4G is pretty good. 5G brought us higher frequencies, as I mentioned earlier. We opened up a whole new, because the 4G spectrum, there was so many people using mobile phones and so much data traffic now going on over the phones, that 4G started to become saturated. And 5G added this higher frequency band that wasn't in use previously. Plus it brought new techniques like beamforming with phased array antennas, and generally just faster data and the ability to handle far more calls simultaneously. And that brings us up to the modern day.
But that's essentially, so in terms of use, like 5G is, you're not really going to notice a huge jump unless you're doing really specific mad stuff on your phone.
I mean, if you're in a very dense city, you will have fewer problems with congestion, with dropped calls and poor quality calls and stuff.
Yeah.
But the other benefit outside of that is faster data. Right. So it's in pound for pound. This is where comparing apples with apples and any other analogy you want to think of. You're going to get like maybe 2 to 3 times the speed of 4G on a 5G data connection. And finally, we have come to the end of part 3 of our 2-part exploration of radio technology. Wow,
that was a lot of information in there. I don't think we'll be given a test on this one.
And don't forget to check out our website on www.enoughwiththescience.com, where you can find transcripts of all these fantastic episodes.
Yes, you can leave us a review and tell all your friends about us as well. And join us next time when we will have another very interesting topic to go through.
Yeah.
Nothing to do with radios or mobile phones, please.
Yeah, no, not for the next 5 years, they're banned.
Thanks for listening.
Yes, indeed. I'm Senan. Have a nice weekend.